If we were to place a giant cylindrical tube around a structure over 300 meters tall, would you believe that the invisible air trapped inside actually weighs more than the entire metallic framework of the building itself? It sounds absurd, yet mathematical calculations prove this to be an absolute truth. This minimalist and highly intelligent material distribution is the exact key that grants a colossal structure its superior resilience to adapt perfectly to nature.
To understand this miraculous distribution, we must explore a visionary engineering mindset.
At a time when the majority believed that a timeless monument must be built from dense, massive stone blocks, a French engineer proved the exact opposite by erecting an open-work iron lattice structure, optimizing mass while achieving superior load-bearing capacity and resilience. Today, we journey back in time to uncover the construction of an iron structural marvel that was once met with fierce skepticism and harsh criticism, yet shattered the engineering boundaries of its era to become an enduring icon, the Eiffel Tower.
So, how did the journey to find the answer to this publicly challenged problem begin?
The story begins in the final years of the 19th century as France prepared to host the 1889 World's Fair to commemorate the 100th anniversary of the French Revolution. To assert its industrial and scientific supremacy, the French government launched a competition to design an iron structure on the Champ de Mars, with a target height of 300 meters. At that time, no man-made structure had ever surpassed the 170-meter threshold, with the world record held by the Washington Monument in the United States. This challenge immediately faced massive skepticism from experts. Amidst this backlash, Alexandre-Gustave Eiffel, a 53-year-old civil engineer renowned for his large-scale metallic bridges, confidently proposed his design. Together with his associates, engineers Émile Nouguier and Maurice Coquelin, alongside architect Stephen Sauvestre, they refined the blueprints to optimize both engineering and aesthetics. Out of more than 100 proposals, Eiffel's four-sided iron lattice tower design was selected in May 1886. However, the project instantly faced a wave of fierce opposition from Parisian artists and intellectuals. They signed a petition to the government, criticizing the structure as a giant factory smokestack or a hollow skeleton that would deface the beauty of the city. Local residents even feared that this 1,000-ton tower could collapse onto their neighborhood. Despite intense public pressure, Gustave Eiffel stood firm by his mathematical calculations and officially broke ground on the project on January 28, 1887.
With blueprints approved, the engineers faced seemingly impossible mechanical challenges.
To turn the drawings into reality, Eiffel and his team had to solve three massive engineering hurdles: stabilizing foundations on weak soil, ensuring absolute precision during assembly, and controlling wind pressure. The first challenge lay at the two tower bases facing the Seine River, where the soil consisted of soft, unstable alluvial silt. To ensure foundation stability, Eiffel implemented compressed air steel caissons, an advanced technology borrowed from bridge construction. Laborers worked inside sealed metallic chambers, injected with pressurized air to keep water out. They excavated deep into the bedrock below before pouring solid concrete foundation blocks. The next challenge was fabricating and shaping 18,038 puddled iron components, a resilient material that was the predecessor to modern steel. To ensure every part fitted together flawlessly, Eiffel established a rigorous quality control process at his factory in Levallois-Perret. Each component was individually engineered and calculated to a precision of 1/10 of a millimeter, based on more than 5,329 detailed blueprints. When transported to the construction site, the components arrived pre-drilled and pre-assembled into modules roughly 5 meters long. The assembly process demanded absolute precision. As the four tower legs inclined inward, the ultimate problem arose: how to make them align perfectly at a height of 57 meters to form the first platform.
A tiny deviation at the base could result in a misalignment of several meters at the top.
Eiffel solved this by erecting massive wooden scaffolding to support the legs, while placing sandboxes inside the support pillars to adjust the height by releasing sand. He also equipped each corner of the tower legs with hydraulic jacks, capable of lifting up to 800 tons. Thanks to this system, engineers meticulously aligned components weighing hundreds of tons, allowing the four legs to lock together perfectly in March 1888.
But the greatest pressure lay not below, but in the violent gales above.
The higher the tower climbed, the more wind pressure became the primary force acting upon the structure. In an era when aerodynamic theory was still in its infancy, Eiffel designed the tower's silhouette following an exponential mathematical curve. The tower flares out wide at the base and tapers as it rises, effectively dispersing wind forces and transferring the weight directly into the ground. The open-lattice structure, featuring thousands of voids, allows powerful gusts of wind to pass straight through without facing major resistance, keeping the tower steadfast during severe storms. Connecting these components also required exceptional craftsmanship, utilizing 2.5 million red-hot rivets. This process was executed by highly synchronized four-man crews, one to heat the rivet to a glowing red, one to slot it into the drilled hole, one to hold the head in place, and the last to hammer the opposite end flat, creating a permanent bond as the metal cooled and contracted. Throughout the construction period, which lasted 2 years, 2 months, and 5 days, workers endured extreme heights during the harsh Parisian winters. Yet, Eiffel's strict safety measures kept workplace accidents to an absolute minimum. His scientific organization transformed the site into a highly efficient machine, requiring only 150 to 300 workers to complete a monumental workload.
The inauguration day arrived, yet the fate of the tower was almost cut short permanently.
On March 31st, 1889, Gustave Eiffel and a delegation climbed the stairs to raise the French flag at the summit, officially completing the structure. At that year's World's Fair, the Eiffel Tower instantly became the centerpiece, drawing nearly 2 million visitors. Steam-powered elevators installed inside the legs allowed visitors to experience panoramic views of Paris from above, generating a massive revenue stream that fully recouped the 8 million francs investment within just 1 year. The entire tower structure utilizes 7,300 tons of puddled iron, with a total mass of approximately 10,100 tons. Thanks to the intelligent load distribution lattice design, the pressure exerted by the tower onto its 125 square meter base is equivalent to that of an adult sitting on a chair. Granted only a 20-year lifespan, the tower faced demolition in 1909. To save his creation, Eiffel proactively transformed the tower into a center for scientific research. He self-funded a meteorological laboratory, an astronomical observatory, and installed a wireless radio antenna at the summit in 1903. The ability to transmit signals across hundreds of kilometers proved the tower's strategic military value. During the First World War, the radio station intercepted crucial enemy transmissions, helping the French military make timely tactical decisions. Consequently, the demolition plan was permanently scrapped. Spanning over a century, the Eiffel Tower has become the cultural symbol of France, recognized as a UNESCO World Heritage Site. To protect the puddled iron structure from the corrosive forces of time and weather, professional crews apply 60 tons of specialized paint across the entire surface every 7 years. To date, the monument has welcomed over 300 million visitors, standing tall as living proof of the ultimate synergy between engineering science and practical execution.
Defying all skepticism, this grand monument has left an invaluable lesson for future generations.
The journey of the Eiffel Tower from the drawing board to the structural field confirms that when scientific solutions are applied with unwavering resolve, mankind can turn the impossible into reality. Gustave Eiffel's innovative thinking and decisiveness in the face of contemporary doubt remain a priceless lesson for generations of engineers to come. Thank you for joining TitanWorks today. If this video brought you valuable insights, please hit the subscribe button and turn on notifications so you never miss our upcoming analyses of the world's greatest engineering marvels. Don't forget to leave a comment below with your perspective on Gustave Eiffel's design, or suggest the next masterpiece you want TitanWorks to uncover. Goodbye, and see you next time.